Okay, so we're going to continue with magnetic materials. And what have we seen so far? We have seen that currents, total current vector can be broken into a bound current due to magnetization. And the other one, just like in the dielectric material, we're going to call it free. There, of course, we had free charge density and bound charges. Here, they're just currents. And the currents are given by, well, this is the current itself, and the special case, which can be used using delta functions as well, m cross n. This is, of course, the outward pointing normal. Unless specified, these guys are always outward pointing. And these are bound. Okay. So we have that the curl of B is mu0 J, which now becomes mu0 J free plus J bound. I'm going to do two things over here. I'm going to bring the mu0 to B, and then I'm going to write this, and you'll see why. It's nothing. So you have two curls. A good bit, there's a lot of physics going on, but behind the physics, now you know there's vector analysis, vector identity, and that's literally it. Outside of that, don't forget we did separation of variables, and we solved PDEs as well. Okay. So now we get curl of now everything is in terms of the free currents that you control. So it makes sense to call this by something. Just like we had the displacement vector, the symbol we use is H, and I cannot remember what it's called. I don't recall ever committing that to memory. Let's see, what did he call it? The quantitative parenthesis is designated by the letter H. H plays a role. Did he call it anything? If you find that term, let me know. I always call it the dual field, something dual to the magnetic field, but I don't know if that's true. That seems like something people would have taken great interest in the 1940s or something to name it. But now we get a nice expression in terms of free currents. So we maybe, he calls this deceptive parallel. See, Beard-Savat's law says mu0 over 4 pi equals what? J cross, so J prime d tau prime, correct? Over sources. But we may be tempted to write, well, what would our temptation be? How would the expression, the temptation, differ from that? the mu zero would disappear, right? We would be tempted to write this, and I've used that word over and over again. But this is not in general true, because this is true Biot-Savart's law also contains this information. Remember, a vector field is described by Helmholtz's theorem by defining its curl and divergence. So this expression contains curl and divergence. So this can only be true if divergence of H is equal to 0. Well, when is that the case? Well, that means divergence of that should be 0, because that's what H is. There are two objections to this. Suppose you have a material, and this is not the biggest objection. You know, here you might have mu 0, and no, here you might have a mu 0, and here you might have something else. Yeah? It may not be free space, and we'll talk about that as well. We had permeability and permittivity, but we had permeability of free space and permeability of certain materials. Or, sorry, permeability. This time it's permittivity. We may have, mu 0 here and something you've not seen, just a mu, some new mu for a new material. So when we have that, across the boundary, the mu may not be continuous. Yeah? So the problem is, well, there are two problems. So one, mu may not be continuous. So we don't know how to take the divergence of that. The second problem is divergence of M in general. Oh, I should say in general. But for some reason, if suppose it's uniform magnetization inside a material and mu is constant, then some expression like this may be possible.
The reason why we don't have a mu term outside of our H term is because the handling of the units and things comes from H itself, that mu naught.
Right. So the mu naught disappears, right? Because we divided B by mu.
And then it would carry over to the Biot-Savart analogy.
Right.
Like we don't have like a mu.
Right, we don't have, yeah. But, so not true in general. Well, it's true if divergence of H is 0. Whenever that's the case, then it's true. So what I want to do is do a couple of problems, but obviously I want to mention linear materials. So what's the, I want to discuss a little more of example 6.2. That's why I'm going ahead and describing so what is it? Magnetic susceptibility, linear media. That's it. do. So we said, don't write this part down, for dielectrics. What did we do? We said this was proportional to E, and we used the proportionality constant. I forget what we used, but
Is it alpha?
could it be? Yeah, that sounds about right.
It wasn't chi is later down the line.
Yeah. Maybe it was chi.
Introduced a lot of constants in that.
Yeah. Yeah, that's right. We introduced a lot of constants, and we're going to do exactly the same. So in this case, we want to do those materials that respond to linearly to magnetic fields, where the magnetization would be proportional to the magnetic field. That's what we mean by linear material. So the symbol here is chi m. We could choose B or H. They're all proportional to each other. So, but this is very much part of the tradition. Huh.
So it self-references itself.
No, this is a relationship between M and H. There's no M on the side. I mean, in any of this.
Isn't there any H outside of H itself?
Correct.
References itself.
Well, so here it is. H is equal to mu 0, what is it? No, B over mu 0 minus N. So if B is in the same, if M is in the same, so this is what you want to do, right? We won't do this, but I'll tell you why it is a good question that you're asking. This is what you want to do, right? If M is proportional to B, then M, B, and H are proportional to each other, right? So now we can pick either one. Yeah, only because if they're proportional, they're all proportional to each other. The only thing that can happen is plus or minus. So it is tradition to call this H. It has a term for it. Chi m is magnetic susceptibility. Ooh, I have to spell susceptibility. Is that right?
It must be a C, or it's SCE.
S-U-S-C-E. Are you sure? Did you just know that, or
I knew it. I looked it up.
you looked it up? Okay. Good, good. So then, we can find a relationship between, hold on, what do I want to do? B and H.
There's also the T that's followed by an I.
T will,
Everything's falling apart.
is that right?
Yeah. Who looks better?
Okay. All right. So then let's do this. H is equal to B over mu 0 minus, what is it? Chi m H. And I have B equal to H. What is it? One plus chi m mu 0. Yeah? So naturally, what we would want to do is call this guy mu. This is permittivity. Not of free space, but of the dielectric. Let me make sure. And mu, no. This is permeability. Oh, I'm not going to spell this. Martin, could you tell me what it is? Thank you, Chip. There is an ability in permeability, which I lack. Okay.
The I's and A's with mobility will get you sometimes.
And I'm especially bad at, I'm hoping for, if I spell it wrong, it should underline and then click. It gives me the right spelling. I mean, smart boards do that, but I hate smart boards in general. So remember, we talked about paramagnetic and diamagnetic stuff, material, right? In particular, if you have diamagnetic, chi is going to be a negative number. Copper is diamagnetic. It's very weakly diamagnetic, but nonetheless, a metal that we use all the time is actually a magnetizable material. But thankfully, it's very weak. Okay. So we're going to solve example 2 now, 6.2. And I'll bring in all of these features. Okay? So what is example 6.2? There it is. You have a long copper rod. As far as we're concerned, it is just infinite, right? Just to make life a little easier. And there's a current. There's a free current. And the free current is given to you. It is uniformly distributed. Yeah, IF equals constant. The question is, find H everywhere. Yeah? Now remember, Ampere's law. I free enclosed. Okay? So this is the enclosed. Okay. What do you think the components of H? One of the components to me is clearly 0. I'm going to use cylindrical coordinate system. Which is the one that is clearly 0? Chip, I want you to answer this because we had The same conversation.
Well, on the test, I thought that.
Oh, nothing to do with the test. We're not discussing. So let me put this in perspective. What we have S in S hat plus H phi hat plus H z hat is what we want. This is the most general. Which one is immediately zero?
I want to say Z, but I know that you said S was the obvious one.
S is the obvious one. Because if it is pointing radially outward, and if I change the direction of the current, then it would be pointing inward. But outward and inward is a physical effect. It shouldn't depend on which way the current is flowing. Because you can stand upside down and look at it. It shouldn't change the direction. So this guy is zero. It is true that that is zero. But what made you say that? I'll tell you what I know. I know that if I take any loop in this direction, or even far away, and I integrate, since this is an Amperian loop, I can pick the direction of the loop. It doesn't really matter which way I go, clockwise or counterclockwise. But there's no current flowing out of this. There's no contribution to H dot dl here, because we know that S direction is zero. So that means whatever H is here must be here, must be here, must be here, must be far away. So I know this. H phi hat plus some constant. The entire universe, because of the existence of one infinitely long copper rod that goes from minus infinity. I mean, there could be right beyond the Andromeda galaxy, there could be like an infinite copper rod going from one end of the universe to the other. And then what we're saying is the entire universe gets a constant H0. Now, Griffin says, well, that's zero. I don't know. If you think of
I guess it just, if it's like infinitely long when we do that, it doesn't make sense to me that.
it should have H infinitely far away. You're absolutely right. Doesn't make sense to me, but we have to do more than that. So yeah. So it is very plausible that H0 is zero. In fact, we're going to get it to be zero. Okay, no problem. Let's leave it there, and let's see what happens. All I know using, so how did we figure out this is a constant? Do you get that?
My reasoning has always been from the curl
Yeah, I mean
to enforce the because if it's non-constant, then
Yeah.
it'll play with the curl.
it doesn't affect the curve.
Right.
Yeah,
Because it's constant.
because it's constant. Yeah. No. But how did you get that it's a constant? Did you follow my argument? H in this loop is zero. H dot dl. But there's no contribution from this side and that side. So this side minus that side should be zero. So this is equal to that. And same thing. This is equal to something further away. Certainly, if it's infinitely long, it cannot depend on the z coordinate as well. Okay. This is easy to obtain. How do you obtain this? You obtain using that. So let's do H out Euclidean loop. I'm going to do this. And then I get h phi times 2 pi s is equal to I, which implies h phi equals I over 2 pi s. Let's do h in. H, not h vector. So h phi times 2 pi s is equal to I, but not all of the current flows through this loop. What flows through that loop is pi s squared over pi, what's the radius of the rod? Is it r? Yep, r. Pi r squared. Of course, the pi's cancel. And then h phi is equal to I s over 2 pi r squared. Is that clear? Or did I do my math wrong?
No, how do we have the pi r squared in this case? We're inside.
If we're inside, it's the whole thing is the free current. But if I take this loop, how much current goes through this area? This area divided by total area. It's only that fraction of it that will flow through. Yeah? So I have found a way to take a simple problem and write it in the most complicated way, which is I over 2 pi, I mean, Griffiths might even laugh at me for doing this. What do we want? No, we want H0 to be 0. That's the correct answer if you look at Griffiths. H0 to be 0. Yeah. We have to work that argument. Outside the rod, what is B? Outside the rod, M is 0. Yeah? Therefore, B is equal to B out. U0 times H. So I want you to think about it and come up with a different reason, if you can, than what I'm going to present. I'm going to argue now that and we'll get the diagram in the textbook as well, that H0 is 0. I'm going to look at the inside. M inside is what? Copper is diamagnetic, right? So it's going to be some, I'm going to put this negative explicitly, and then I don't want, it's not, it is chi-m, but chi-m is a negative number. So maybe I could even put this, yeah, that's even better. So have my M, so that is M is equal to negative chi M. H in, what is H in? It is IS over 2 pi r squared phi hat plus H0 z. Let's compute the bound currents. What is J bound? Curl of M. We can take the curl of M, but you know how to take the curl of M. Actually, I didn't bother to take the curl of M. Let's do it old-fashioned way. What is curl in cylindrical coordinates? So I have negative chi of M. Look at this. Tell me what the S component of curl of M is going to be. That is 0 because I have to take the the zth derivative of phi, which is 0. What about the phi component? There's the z component. That too is also 0. What about the z component? What should exist? I should be able to take, it is 1 over s dds of s times v phi times I s squared over 2 pi r squared. And that's going to be the z component, correct? So that is equal to s, the 2's would cancel, the s would cancel, and I would get I over pi. Please check, Chip, Martin. I don't have the exact curl written out. Correct? Okay. And then, what about the boundary current, KB? That's easier. KB is equal to M cross N, which is in our case M cross S hat. That is equal to minus chi of M I s over 2 pi r squared. What is phi hat cross s hat? Phi hat cross s hat is negative z hat. Plus chi m h0. What is z hat cross s hat? Yeah? Okay. Now, here is a long-winded argument. Outside the wire, what are the sources of B.
Well, this much of it come from.
There are three sources. We'll have I times Z hat, the free I. Then there is J and K along the Z hat direction. J and K along Z hat direction. And the third one is K along phi hat direction. K along phi hat is like a solenoid. Correct? This is just current along Z hat. If you have a current along Z hat, what's the B outside? Ampere's law? S, right?
Yes.
It's along what direction? Phi hat. If you have a solenoid, what is the magnetic field outside?
Zero.
Very good. Therefore, so imply B out has a phi hat component, implies B out is 0. That means B out must only have a phi component. I have erased everything that I need. Oh my goodness, I have erased. I will ask your help to write this down because that's also important. B out should be of the form. What did B have for B out?
You know, IS on the top over 2 pi r squared. Yeah.
Plus,
H minus Z.
what does that imply?
H minus 0.
As needed. Now, I have KB over here. What is JB that I just erased?
Negative absolute value of pi over pi r squared.
I over pi r squared Z hat. Okay, now I want to draw a picture. I've done quite a lot. So, and I've erased this is one of those lectures where I wish I had like a wraparound board, but I don't. So any questions before I draw a diagram?
I know we talked about this, I'm sure, but why were we so set on having H not equal to 0?
Because the universe won't be filled with an H naught if you have one copper wire in a galaxy far, far away.
Okay.
And that doesn't make sense that there's a uniform.
I mean, to me, it makes sense that if there was an infinite wire in Z direction,
Yeah.
but where you are in relation to Z I mean, it makes sense that that wouldn't matter because it's infinitely long in either direction.
Yeah, it wouldn't depend on Z,
Yeah.
but it could have a Z component that doesn't depend on Z. Yeah. I'm not saying there's a Z dependence. It's easy to see that there's no Z dependence.
Yeah.
But the question was, is there a Z component? And I was just forcing myself an answer to see, insight is good, but we have to build insight through hard work, right? So now, a picture is worth 1,000 words. And I looked at this picture, so when I remember years ago when I first was writing up notes to this, and he had this, nice picture, no explanation. So it took me a while to crank this out, so every time I teach this course, I abuse my students by just going through this long-winded calculation. So we know that there's current in this direction. Yeah? Now let's talk about magnetization current. Which way is J inside?
Or Z out here.
Yep. These are the 3 different currents. What about K on the boundary?
Yeah, on the boundary and then Or
No, it's 0 is now 0, mind you.
so,
Yeah, there's no solenoid current, so to speak, right? It's along the plus Z direction. Now look at Griffith's textbook. If you have it on your iPad, you will find that this is consistent. This diagram is consistent. And then he had another rectangle drawn that I was wondering what this was about. And he had arrows pointing. Yeah. I was thinking, what could that be? This is the magnetization loop. This would mean that M is pointing that way, or M is this way. What was H? It was what? I
in
S over in 2 pi r squared phi hat, correct? So M is minus chi m I s over 2 pi r squared phi hat. So M is pointing this way. Over here, it would be just pointing out of the board. That is that picture over there. See, if M is pointing out of the board, the current loop is this way. This completes the diagram in the problem. Yeah? Everything consistent? So I may delay the starting of the next chapter on electrodynamics by one more day. I'll just spend a little time doing problems. So in all this problem, in the entirety of this problem, constantly set H0 to 0, because now that we know that, all the answers become somewhat simpler. So J is this, K is that, and there's no solenoid current. All currents are either up or down. Yeah? The magnetization, because it's diamagnetic, it points against the direction of H. So and magnetization is a small number, so H and B continues to go along the plus phi hat direction, and M goes the other way around. As a result, the magnetic loops are this way. So over here it would be this way. Over here it would be not this way, but the other way. So that M is like this, like that.